Hi guys, so this is going to be the next lecture in our quantum mechanics series. So previously we said that in quantum mechanics revolves around a thing called the wave function, and we said that the wave function, denoted by psi, is a function of x, which is position, and t, of time. Okay? And we said that this psi is governed, its time evolution is governed by this equation, the Schrödinger equation, which is negative h bar squared over 2m, just a constant, partial of psi, second partial of psi, with respect to position, squared, plus the potential, a function of only position, is equal to ih bar, where I is a complex number, partial of psi with respect to time. This shows the time evolution of the wave function. It's pretty important. We're going to get back to it later in this lecture. And then we said we can separate the psi. Oh, then we talked about a statistical interpretation, like the mod squared of psi is the probability density. Shows the probability at different times. And we also said that the expectation value of, say, position is equal to the integral of psi smushed in with this position, except one of them is complex conjugated, dx. And we said that the position operator, we talked about this concept of operators. We said the position operator was h bar over I, then the partial with respect to x. We said that there was an important operator called the Hamiltonian, which represents the energy of the system. I'm just going to put them in parentheses. That's equal to negative h bar squared over 2m, partial squared over partial x squared, plus v, and so on. We talked about all the statistical interpretations. Most of it was credited to this man named Niels Bohr. No, not Niels Bohr, what am I saying? Max Born. Yes, him. And you can look that up on your own time. And then we said that the wave function of x and t, could be broken up into a function of x, psi of x, and phi of t. It's called, this method of separation is called separation of variables. And technically this should be a capital psi, but I'm lazy with my notation, so I'll forget to write it a lot. And then once we plug this back into our Schrödinger equation, we found that the time independence was in fact an actual answer, specifically e to the negative I et over h bar. And e was our separation constant, but then we found out it was our energy. So the generalized wave function psi of x and t turned out to be psi of x times e to the negative I et over h bar. And we found out that any wave function will have the same time evolution because of this exponential right here. So now let's get into another important concept called superposition in quantum mechanics. Now this concept is pretty important, so I'll take a couple minutes describing it. So superposition, what does it mean? What is it? Superposition is basically a linear combination. Like, say we had one psi over here, and we had another one 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 here, and so on and so forth. We can make a generalized wave function with no indices, and then, if we kept going with this numbers, we would just get up to a general one, psi n of x. So if what I was saying is that we can make a generalized wave function with no indices, no n's, just of x and t, such that it is a linear combination, a linear superposition of all of these stationary states. So what I mean by this is that a superposition, we're summing them all up from n equals 1 to infinity, encompassing every single stationary state, a superposition of all of them, of the regular stationary states, and then since there's a time dependence to the general wave function, we add this time dependence that we had previously. And now, when we have a sum and we're doing a superposition, we have to tackle on along this C of n. These are just going to be our constants that we're going to find out. Because every wave function has a different set of constants. Because if we had no constants, then every single wave function would be the same. Only this thing would be different. And our constants, which we will see later, we're going to be using this thing, a method by this guy named Fourier, called Fourier's trick. That's what we like to call it. And then we're going to find out that C of n is actually the integral of psi of x times 0 times, it's actually the integral of psi of n times 0 times the stationary states, but except they're complex conjugated. And of course this is dx. And then also, just a general way to write it, we can, instead of writing psi of x and 0, which is going to be relevant in our case, we can write it just as any function f of x. And of course this is from negative infinity to positive infinity. So this is going to prove important to us, and this is actually an introduction into what is called the Fourier transformation. Fourier transformation. We're transforming f of x into c of n, and we can do an inverse Fourier transformation where we transform f of x, c of n in terms of f of x with this integral sign. So it's pretty important, but it's not going to be something that we're dealing with today. So let me just move this up a bit. Okay, we'll work over here. So we said that there's a superposition. We can make a generalized wave function in terms of a superposition of the stationary states. So let's just do an example for real quick. Let's say that psi of x comma 0 is equal to just a basic c1, which is a constant, times psi 1 of x, plus c2 times a constant, this is a constant, times c2 of x. And we're just asked to find psi of, we want to find it at any time t, basically it's time evolution, and we also want to find its probability density. So the former is not too hard. We just tack on this time, which we already know is constant with everything. It's right here. It's just the e to the negative iet over h bar. So we get psi of x and t is equal to c1 times psi 1 of x times e to the negative iet over h bar plus c2 times psi 2 of x times e to the negative iet over h bar. And that's it, we're done. Correct. So this is an example. And now we want to find its probability density. And we're doing the same thing as we did previously. We're just plugging it in. So psi squared would just be this squared, c1 psi 1 e to the negative iet over h bar plus c2 times psi 2 e to the negative iet over h bar. It's just this. And then we're multiplying this by, let me just do it down here. We're multiplying this by the complex conjugate. So c1 psi 1 starred e to the I et over h bars, because the complex conjugate of an imaginary number, you just take in the opposite sign. And then this is plus c2 psi 2 star e to the I at over h bar. Okay, and after we do that, we find that it's a really long thing and you can calculate it easily. What I mean to say is that given any condition, starting condition, time equals 0, we can find how this wave function evolves under time due to the fact that we can write the wave function as a superposition of its stationary states. And everything from there, such as the probability density and everything else, moves on from there. So I've just made a little bit more room for myself. Alright? So now let's get back to this time-independent Schrodinger equation. Time-independent Schrodinger equation. We said it was h hat acting on psi is equal to e psi. And if we expand it out, this h hat, we would get negative h bar squared over 2m partial squared psi over partial x squared plus v acting on psi is equal to e psi. Alright, and we said that we couldn't solve this because we had this potential and we didn't know what it was. Depending on the potential, we can solve it for different solutions. So now I'm going to introduce you to a potential we're going to work with for this lecture. It's called the infinite potential well. And this meaning is going to show itself in a little bit. So let's say I define the potential, which is dependent only on x, and this is equal to 0 if 0 is less than x is less than a, and a is just a number that we'll see shortly, and it's equal to infinity otherwise. So this is weird, isn't it? Like, let's just graph this. Let's see what this actually means. Let's graph it. So we have our x over here and our y over here. So let's see. We have, let me pick a color. We have 0 if x is greater than or equal to 0 and less than or equal to a. So let's pick a point A right here. So it's 0 over here. And this is, of course, the origin. And then it shoots up to infinity otherwise. So it shoots up like a rocket. Let me just draw that better. It shoots up like a rocket to infinity if it's not 0, if it's not from 0 to a. So from here it's 0, and from everywhere else it shoots up to infinity. And what this means is it's an infinite potential because it's going all the way. It's never stopping. So we get this well over here, and this well is going to be our potential where the wave function is. And we're going to see that the wave function is quantized, and we'll see what quantized means later. But that's very important because quantum mechanics has quantized things such as energy, such as the wave function, such as anything. So we said it's 0, and that's the only thing we can work with. We can't work with infinite potentials. Like, what is that? We can't work with that. We can only work with it if it's 0. So what does this equation become? If the potential is 0, it just becomes negative h bar squared over 2m partial psi over partial x squared, partial square psi, I mean. So this thing just cancels out completely, equals e of psi. Now I just want to isolate psi, so I multiply this by 2m over negative h bar squared, 2m over negative h bar squared. What we get is this thing cancels out. We get partial squared psi over partial x squared is equal to negative 2m over h bar squared